Okay, so let's get started. I think some people are going to trickle in. We'll start just to stay on time. So just to continue the lecture from last time, we were talking about remote procedure calls. What is the abstraction of an RPC? Essentially, the ability to invoke a procedure or a method in another process, possibly on another machine. We talked about how RPC runtime systems work in terms of having stubs that do all of the work on behalf of the programmer, the network communication, packing and unpacking arguments, and so on. Okay, I mentioned this notion of binding, which basically says when a client starts up, how do you locate where the server is? If you know the IP address of the machine, there is a service called a port mapper that runs on each machine. That supports an RPC runtime system. That's a directory service where a server can register its port. So if you know the machine address, you can just contact the directory service, the port mapper on that machine, and say what socket does it listen on. Okay. So that's basically the notion of binding. The server has to basically register itself when it starts up, and before you send the first RPC, you have to look up the port mapper and find out what IP address the server is listening on. That can then tell the stub what socket to connect to get to the server. Okay. The other option, of course, is to use well-known ports, as we were talking about last time, saying there are RPC mechanisms that work over HTTP. When you hear of web services, when one web application can make calls to another web application, it typically is done over HTTP. Okay, there's an interface that's exported, there are calls you can make that allow you to invoke methods. Okay, so that's another way. In that case, the port number is well known as well. Okay, so this is something you should keep in mind. Okay. Now, the last point we want to look at here before talking about RMIs is what happens when there are failures. Okay. You have a client that has made a function call, a remote procedure call on the server side. So the client can fail, the server can fail, or the network packets can get lost. Okay. And you need to have predictable behavior in scenarios where such failures can occur. Okay. When you have local procedures, then typically you don't need to worry about this kind of problem. Okay. If something goes wrong, the entire program crashes, because it's when you make local procedure call, that's single process. Okay, multiple threads maybe, but single process. And if something goes wrong, your entire process crashes. There's nothing really to do other than possibly restart your application. Okay, but when you have client-server application, the client or the server may fail, or your requests might not get there, replies may not come back. Okay, so you need to be able to figure out what to do. Okay. Few things are fairly straightforward. So if the client is unable to locate the server, if the server is not running at all, okay, the client tries to make an RPC call, but the server is not executing. That's a simple error message. There's nothing you can do other than to say that's an error, server is not running. Now suppose a client and server are both running, but there's something goes wrong on the network. Okay, you send a RPC request, that packet never gets to the server. Okay, or maybe the packet gets to the server processes it, but the reply never makes it back. It's lost on the network. Okay. The question is, what should we do in that scenario? Okay, so any thoughts here? Okay, you can use a timer. That's what says on the slides. It's good. Okay, so that's the straightforward mechanism, but I'm looking at other ideas. So you can, of course, wait for a while. If you don't hear back, send the request again. The client will make an RPC call and say, I wait for 5 seconds. If you do not hear back within whatever time you have specified, you resend the call. Okay, so that's one approach. So, and that works whether the request got lost or replied, with one caveat that will come to in a moment. But what other things could you do?
Can't we leave that to the TCP layer?
Okay. Can we not offload that to the network? So good point. Saying, why should we bother? Okay. Why not use a network protocol that will deal with that issue for you? Okay. So if your RPC system is running over TCP, right, The abstraction that TCP provides you is basically one where packet losses are dealt with by the transport layer. So you basically get a error-free, I shouldn't say error-free, but basically an abstraction where there are no packet losses, because TCP is going to deal with retransmissions and so on. So any packet that is sent will arrive at the other end eventually, with after some number of retransmissions and so on, so long as both endpoints are aligned. So good design choice is to say, why do you want to do this in the RPC system? Leave it to the network. Choose a transport protocol that will deal with network packet losses for you. So you, the RPC system, runtime system, doesn't have to deal with it. So that's a good point. And indeed, most RPC systems will look at it. This timeout mechanism aspect is only relevant if you are running your RPC system or UDP. Right? UDP is another transport protocol. If you know anything about networking, you will know that in case of UDP, there are no guarantees. You just send a packet, it may or may not get there at the other end. And packet losses have to be dealt with by the application. Right? So if your RPC system is running over UDP, you will actually have to time out and retransmit. If your RPC system is running over TCP, you will not have to deal with it. So the network will deal with it. Okay? There are of course pros and cons. Okay? If you remember when I was talking about client server TCP, I said every time you make a connection, okay, you have this three-way handshake overhead. Okay? So if you're running over TCP, you're going to pay the price of setting up a connection and tearing it down. Okay? If you are on a fairly reliable network, you might want to take the chance and just send over UDP. UDP, there is no handshake. You just, when you want to send a packet, you just send it. Okay? There is no extra overhead, no extra packets have to go back and forth. Okay? So on reliable networks, you might get away by not paying that extra price, but you have to deal with occasional losses. So there are trade-offs. Okay? If you want to ask more of the network will impose more overhead on the system. If you ask less, the system has to do more. Okay? That's basically the point there. Then you have to choose your protocol carefully. Okay? The other point is, if you use TCP, there's no problem. All packets that are sent eventually make it to the destination, and nothing more has to be done. If you are using UDP and you are retransmitting, you are making a request again, you have to keep track of what might happen at the server. In particular, if the server is stateful, you have to make sure that your RPC calls are idempotent. Right? Meaning re-executing the call doesn't cause problems or errors. Okay? Think of an RPC call that says deduct $100 from this person's checking account. Let's say you are at an ATM, you're withdrawing $100. Okay, and the ATM is running a RPC application that's making a RPC request to the backend database, which is storing your account information. Right? So you send a request saying deduct $100, this person has withdrawn $100. Okay? Let's say the request gets there, the database actually performs the requested operation and sends back a reply saying done, and reply gets lost. You time out and resend that request and deduct $100 again, okay, and then you will re-execute. That's not idempotent because it's changing state at the server. Doing this operation twice will result in an incorrect state as opposed to doing it once. Okay? So you have to deal with this issue. You have to make sure if you retransmit, that call has to be idempotent. You have to either make sure the calls are idempotent or track whether the previous call has actually executed and not re-executed. Okay? When we come back to fault tolerance, okay, that's I think chapter 7 in the book, we will revisit designing fault tolerant RPC system. But just keep this in mind, okay, what would you do. Okay. The other thing that can happen is the server might crash while it is executing an RPC procedure. Okay, then what is the client to do? Okay. So, of course, if it crashes, you have to restart it, the server that is. But and then maybe the client might have to retransmit the call, or maybe there's a way for the server to recover. But regardless of what happens, if you design your RPC system with the right semantics, at least the client knows when it got a reply, what has the server done. Okay? And this is referred to as the semantics provided by the RPC system. You can have a number of semantics. You can have something called at least one semantics. In at least one semantics, what that says is if you get back a reply, you are guaranteed that the call has executed at least once on the server. It may have executed more than once, meaning that the server may have crashed. Okay, just before it crashed, it may have finished execution but hasn't generated the reply. It recovers and it restarts that RPC call and re-executes it. Okay. So if you have at least once, that says if you have received a successful reply, your RPC call was executed at least once. At most once basically says that if you send if you get a reply, it has executed at most once. Yeah, and if you actually get a valid reply, that means it would have actually executed once, not 0 times obviously. But it could basically be 0 or 1. 0 means you will get an error, otherwise it's at least 1. Okay, what you want is exactly once. Okay, if you want a good system, but exactly one semantic, that says no matter what happens, server crashes, recover, restarts, if you get back a reply, you are guaranteed that your call executed exactly once. Okay, for exactly one semantics, that's the most desirable from the client's perspective. It doesn't have to worry about, is the server stateful, did it execute it twice, what if my request was not, call was not idempotent, because if you restart the call and it has changed some state, then you may actually get an error. So you have to deal with all of this. Of course, you can say I give no guarantees at all that the server may crash. It's the application's job to figure out how to recover and so on. Okay. Most cases you will get something fairly weak. Exactly once is very hard to implement. You have to deal with all possible scenarios, ways to fail, ways to recover. Anything can happen. So most systems will not take the trouble of providing exactly one semantics, although it may be desirable. Okay. They might actually do something fairly weak which says at least once. At least once essentially is not making much guarantees. It's saying if you get a reply, your call would have at least executed once, maybe more, because you may have crashed or threads may have crashed, it may have restarted, all of those things could have happened. Okay? So commercial systems would provide you somewhat weaker semantics that might not be very desirable, but that's the way it goes. And then the last point is you may have failure at the client. Client made a RPC request. Okay. Before the reply came back, the client has gone down. Okay. It crashed or some error occurred, the client just failed. Okay. What should the server do? Okay, so what do you think should be done first before we decide what the book says should be done?
Wait for the client to get back in touch.
Okay, you could wait for the client to get back. Okay. A server, okay, you could do that, but servers typically don't control anything about the client. Clients could be independent machines. Some client came and made a HTTP RPC call. You have no idea what happened when you try to reply. The client has disappeared on.
Wait for the client to get back in touch with the server.
Okay, you could wait for the client to recover. Okay, just as we waited for the server to recover and send back a reply. That's one design choice. There are other design choices one could think of.
Throw it all away.
Yeah, you could throw it all away. That you could say, "What? It's not my problem. Client crashed. It's client's problem. I have executed the RPC call that was made. If you want the reply, it's here. If you don't want, I'll throw it away." It's also fine. In fact, that's what most systems would do. Okay, because server, you expect it to be running. Clients can come and go. If the client crashes after making an RPC call, it doesn't get a reply. The reply is there, but it is not going to get delivered because the client crashes. Okay. So simplest choice is basically you will be, not worry about it and you will just throw away the reply. Okay. And that's a fine choice. For most small RPC procedures, that would be a fine choice. Okay. Now what if your RPC call you made triggers a long running computation at the server? Okay, this may be a very long RPC call request which may take minutes of computation to generate a reply. Okay. What happens if the client crashes in between and the server can actually figure out that the client has actually crashed? Okay, should it continue executing the request? Should it not continue? You can make different design choices. Okay. First of all, if you have long running RPC calls, okay, most calls may be small, you do some computation and the reply comes back quickly. In that case, if the client crashes, you just ignore. Okay, basically the reply is thrown away. But if there are long running RPC computations, at the server end we'll call these as orphan RPC calls. Okay, there is no client to receive that reply. So what you do is orphaned RPC call. Okay. So essentially what you can do a variety of things. You can do what is called extermination. Okay. This is essentially just going to terminate the RPC call. If you can detect that the client has crashed, because the TCP connection may go away. If the endpoint disappears, the OS is going to tear down the TCP connection. So you will have some indication that client has disappeared, or you could log it at the client stub at the server, or at the client machine, and the client stub, the runtime system can notify you. There may be many ways to signal the server saying client is disappeared, and then you can just terminate. Okay. And then but this will actually require an overhead of tracking on a per client basis what's going on, so that overhead may be high. If you don't want to impose that overhead, what you can do is you can basically divide time into what is called epochs. Okay. So let's say an epoch is 5 minutes. Okay. Every 5 minutes you do a check. So is there any RPC call that has been running for the past 5 minutes? Okay. And if yes, you say this is a long running RPC call, let me actually check if the client is still alive or not. And if not, you are going to essentially delete that computation. Okay. So in this case, you check whether the client is alive on a per call basis. In this case, you do it at periodically once in a while. Okay, so you don't actually check what has happened between 2 points in time. Every once in a while you check, is there something that's running and maybe something has happened to the client? If so, if you detect that, you will terminate. So this is referred to as reincarnation. You can do something called gentle reincarnation, where you can say if the client that made the request is gone away, you can actually broadcast and check if the client has restarted, possibly with a different process ID and so on. And if so, you will try to redeliver once the call finishes that reply to that client. Okay. So in either case, you detected that the client has gone. In one case, you simply terminate the computation. In another case, you try to locate if the client has restarted, and only then do you delete if there's no owner. And expiration is the last method, which says every time an RPC computation starts, you give it a timeout. Okay, you start a timer. Yeah, timer may be 30 seconds. Okay. When the timer goes off, you send a message to the client. Are you alive and are you still interested in hearing back? Okay. If it says, the client sends back a reply saying, yes, I am alive, continue, and get me a reply, you start another timer. Okay, let the RPC keep going. If the timer expires and RPC is still executing, you check again. Okay, so you basically have something called an expiration time, a fixed quantum 2, T, rather, and you explicitly check at the end of an expiration of an RPC call, and keep extending the time. If you pick the timer value long enough, most RPC calls will actually finish before the timer expires, so there is nothing to do. So this will only trigger for really long running RPC calls, and for those kinds of requests, it's worth the check. Okay, so whether the client is alive and whether it's still interested in getting the reply. Okay. So if you are designing your RPC system, you have to think about how you deal with failures of the client, the server, of the network packets being lost into this question here.
Yeah. So in case of the expiration, does the server have to ask the client whether it still wants to proceed, or the client sends a keep alive?
Yes. So question is, if there's an expiration, does the server actually have to ask the client, should you continue, or is it the client's job to say keep going? Okay? You could do it this either way. Okay? Or the basic mechanism is, whenever an RPC call starts, you start a timer. Okay? When the timer expires, you can put the burden on the client to say you should ask the server to keep going. Okay? So you explicitly also keep your own timer and say the timer is about to expire, refresh and keep going. Or the server can check and then do. So in one case, the burden is on the server. In another case, the burden is on the client. Typically, in this case, since we are dealing with client failures, it's better to put the burden on the server. Because if the client doesn't come back to you, you don't know what to make out of it. You could just assume that the client is not interested and just delete the computation. But if the server knows for sure, is good. But either of those design choices would work. Right? So you could just say that burden is on the client. If it doesn't tell me to continue after 30 seconds, I'll assume that the client has crashed or is not interested, and just terminate. Yeah, so you could do it both client driven or server driven. So very quick implementation issue. So as I already mentioned just on the previous slide, you could use different protocols to run your RPC systems. Okay, the original RPC systems that were designed actually ran on UDP, not on TCP. And this was primarily because they were designed to operate in a LAN environment. Okay, clients and server were on the same Ethernet. On Ethernet's packet losses are typically rare. Packet losses typically occur when you go over the internet and some router gets congested and starts dropping packets, or there is an error of some sort. Okay. So on a LAN, UDP works fine, but over time the RPCs have grown in popularity, and you have many client server applications that operate over the wide area, not over local area networks. Okay. So for those kinds of applications, TCP is a much better choice, because you don't want the RPC system to do extra work of trying to deal with failures. You just want a network abstraction, a transport protocol that will deal with packet losses and recover from them and retransmit and so on for you. Okay. But many RPC systems allow you a choice. When you start the RPC or start the server, you can decide whether you want TCP or UDP. You have to choose that as a programmer. Okay. The other thing to keep in mind is that there is a lot of overhead of sending these messages. Typically any network message, not just an RPC message, when it goes from one application to another, you basically have to, the RPC call has to come from the client into the stub, okay? And any parameters have to be copied in there. The server has to construct a message to send to the client, has to send a message, create a message to send to the server. And that will involve copying of any arguments, if there are long arrays of structs, from the stub into the message. A message is then handed to the kernel to be sent. Okay, that's a system call. Typically that's another message. Okay. And from there it gets copied onto the buffer on the network interface card, like an Ethernet or Wi-Fi, where it's sent. So that's one more copy. Okay. And at the other end, when it comes from the medium, you copy it into the card's buffer. From the card you give it to the kernel buffer. From the kernel buffer you give it to the stub. From the stub you give it to the server. So there's a lot of data copying involved. The more arguments you have to pass back and forth, the more the overhead, because there are several copies you have to make, and memory copying can add up in terms of overhead. It's relatively fast, but if you have to do 7, 8 copies for every message that's going out, if you have to pass long arguments or some such thing, you are going to pay the price in terms of performance. Yes, question.
Can we just use pointers?
Good point. So, question is, can you not use pointers? Typically, so I was about to say that this is not specific to RPCs. This is a problem that is true for any message passing, whether you're using vanilla sockets or any other form of communication. When you have a lot of data being sent over a network, this overhead does creep up. And there have been efforts to reduce that overhead. Essentially, there are architectures called zero copy architecture that essentially try to not do these copies but pass pointers. Okay. But that's easier said than done, because when you go cross from user space to kernel space, you are crossing address boundaries. So typically you don't want to pass a pointer to an OS and have the OS dereference a process pointer. Okay. So at least you have to do one copy when you go from user space to kernel space. Okay. Within kernel space, when you go from the kernel to the driver on the Ethernet card, you could possibly pass pointers inside the kernel and not actually make copies. Okay. So you can optimize this copying overhead by passing pointers and not actually copying, remember, except for when you cross from user to kernel space and vice versa. There, for protection reasons, you don't pass pointers. Okay. You certainly don't want the OS to hand a pointer to a process saying, here is a message. Okay, that buffer sits in kernel space. It allows the user process to go and corrupt something in kernel space. You don't, and in fact, the OS will not allow you to access its address space in any case for protection reasons directly. Okay. So you have to be careful in how you pass pointers, but that's really what is done in many systems to reduce this copying overhead. Okay. Very quickly, I'm going to talk about Sun RPC and then move on to distributed objects. RPCs were made sort of commercially popular by what used to be called Sun OS in those days. Today is that OS is referred as Solaris. So many years ago, Sun Microsystem was implementing NFS. We'll come back to NFS when we talk about distributed file system. So to implement NFS, they chose to use RPCs rather than doing socket communication between the client machine and the file server. It's a file server. So clients and servers have to communicate to read, write files, and Sun decided to go with the choice of RPCs. So they built an RPC layer and then they implemented NFS on top. And then they realized that the RPC layer is more generic. So other applications could be written using the same RPC abstraction. So they made tools like an RPC compiler available to programmers. And then people started using RPCs for a variety of other applications. So developed for use with NFS, now widely used in a variety of contexts. As I mentioned, it was originally built on top of UDP. This is because NFS was designed to be a local area network file server net. So as I said, packet losses are rare, so you don't want to pay the price of connection establishment of TCP and so on. But as it stands now, when you start up your server, you can pick, the programmer can pick whether you want that RPC call to go over UDP or TCP. And then the system will do, the stubs will do the right thing depending on what protocol you picked. All of the marshalling, unmarshalling is done. There's a XDR is a standard that Sun came up with, that's called external data representation. Any packets that you send out with arguments in an RPC call have to be first translated to this external format and retranslated back at the other end. This is to deal with heterogeneity, a big Indian, little Indian problem at both ends. It provides at least one semantics, which is basically no guarantee at all. If your reply comes back, you know that the server has executed your call at least once, but maybe more than once. And if you're not idempotent, you may be in trouble. Yes, so that's a quick snapshot of how RPCs came about. If you will program your lab in C or C++ and you choose to use RPCs, this is essentially what you will use. Although this was designed by Sun, now many operating systems, whether it's Linux or BSD or any other commercial Unix-like operating system, including Windows, support this Sun RPC. It's not called Sun RPC, it's just called RPCs, the same interface. So you can just write to that interface and be done with it. If you decide to do Java or some other programming language, you won't use RPCs, you will use RMIs or some other form of an RPC. Okay. Any questions here before I switch to some other small things about RPCs, and then we'll talk about RMIs. Any questions on RPCs so far? Okay. I will mention that lab 1 is out. I just posted it this morning. Okay. So go take a look at it. It does require you to use threads, RPCs or RMIs, okay, and peer-to-peer systems. So you need to go read it. I will discuss it next time once everybody has at least read it once, okay, as to what is expected. Right? So whatever we are saying here, you are going to use in some shape or form in your assignment. So let me talk about some special cases of RPC. So what I talked about is the more general purpose RPC systems, but there are many special cases. The first special case is what is referred to as lightweight RPCs. Okay. Lightweight RPCs basically occur when the client and the server are essentially processes that run on the same machine. Okay. There may be many scenarios that you choose where the server is running on a machine and there's a client that starts up on that machine and connects to the server. You may just choose to write your application as a set of processes. It could be a multi-process server like the one we talked about last time. And then if these processes communicate over RPCs, then you basically have to have a message go from the client process to the server process. But because they are on the same machine, you do not have to pay the full price of actually constructing a message and have TCP process it for you. You can take a shortcut. And the shortcut is basically where rather than sending an explicit network message, you short circuit and just basically pass a buffer from the client to the server. Okay, you basically have some shared memory region where you stick in your RPC request and the parameters and just tell the server saying, here is the request. I'm not going to send it to an explicit message. Okay, so what would happen in this case is you would push your arguments onto the stack. Okay, you would draft the kernel. And the kernel would just take those arguments, the memory region where you push those arguments, and simply change the memory map of the client so that that memory region becomes available to the server. And then the server is going to be told saying, here is a request, and the request is actually held in this memory region. Rather than explicitly sending a socket message or a TCP message, you are essentially passing a buffer from the client to the server. And then the kernel, the server is going to go execute it, and the reply is sent back the same way. Okay, reply is put in that memory region, and then the kernel is going to change that, reverse the mapping so that that memory region again belongs to the client. Okay, so you have the server. This is the server process. This is client process. So the client wants to make its RPC request. You put that RPC request in a memory region. Okay, and then the OS is going to map this memory region into the server address space. So this is like passing a buffer. So this memory region appears here magically. The server can then just go there and take the RPC request and the arguments, execute, send back the return value in here, and then the mapping is taken away so that that page essentially comes back to the client process and you are the reply. Okay. All of this is again dealt with by the RPC runtime system. Okay. The runtime system can decide, should this request be sent as a TCP message from the client to the server in the regular way, or can you short circuit the whole thing and just put the entire request in the memory buffer and just essentially it's just like passing a pointer, except that the pointer is going from one process to another, so you have to do this by taking that memory page and remapping it to the address space of the server. Okay? So if you do this, you have what is referred to as lightweight RPC. It's an optimization where rather you don't pay the price of sending a real network message, which would mean that you have to pay the price of entire TCP/IP protocol processing, setting up a connection from the client to the server, which are on the same machine. It's all unnecessary overhead in this case. Yes.
Does the client know beforehand if the server is running on the same machine or on a different machine? Does the RPC runtime system take care of that?
So the question is, that's a good point, which is, does the client know ahead of time whether the server runs on the same machine or not? So I was going to say that the lightweight, or whether to use this mechanism or not, can be determined at programming time or at runtime. If you know that this application is designed such that the client process and the server process will run on the same machine, you can compile this in. You can say that use this optimization always. Or if that's not the case, you can use a runtime bit to decide this at runtime. So for instance, you put the RPC system, you could design an RPC system where you first find where is the server running. If you find that the server is running on the same machine, then you say, I'm not going to actually send a message, I'm just going to pass a buffer. Okay, this is the client process, that's the server process, and this mechanism is called doors in Solaris. Right? You don't have to worry about why it's called doors and not windows and all that kind of stuff. Okay, so basically a lightweight RPC mechanism where you are passing a buffer from the client to the server, and this could be decided at runtime also. Okay, so you can say if the server is running elsewhere, you will communicate using a network message. If it's not, you're going to use this is unstructured communication. It is not explicit message passing, it's implicit message passing by essentially passing a buffer that contains the message from the client to the server. Okay. So that's lightweight RPC. It's an optimization that is available to you. Okay. Some other specialized form of RPC depend on what semantics you are providing to the client. Okay, in terms of when replies are come back and what does the client do when the request is actually being processed and so on. The best way to see this is through pictures here. Okay. So this is the traditional model of RPC, which we will refer to as synchronous RPC. Okay. Synchronous means blocking. Okay. And what does that mean? When the client has made a request to the server, the client is going to block until the reply of that remote procedure comes back, until the response comes back. This is referred to synchronous or blocking RPCs. Okay, this is what will happen even when you call a local function. You will basically push that onto the stack and execute the called function, and only when the called function returns will the caller continue execution. Same semantics are true here. Okay, this is the caller, this is the callee. The caller makes a call, it's going to block, wait for the reply. When the reply comes, you continue execution. The return value comes back. That's synchronous. Okay, here is another mode of operation, which is asynchronous RPCs. Here what happens is you make a RPC call, a message goes back, you get an acknowledgement. You wait until an acknowledgement comes back saying the call has been, your request has been received at the server. Not executed, just that it has been received. Okay. So once this happens, then the server, the client, is going to continue execution. At some later point, the server will asynchronously execute your RPC call. Okay. And the reply will come back to you asynchronously, and it will trigger an interrupt saying that RPC call that you requested some time ago, its reply has arrived. Okay. So this is asynchronous, non-blocking. You don't block until the procedure is executed. Okay. This is especially useful if the RPC call is a long-running computation. Okay, you can just send that request off and it will do some computation, and the client can continue doing something else. At some later point, the reply comes back, and then you can take the reply and do whatever you need to do with it. Okay. This is referred to as asynchronous RPC. Here is what is referred to as, this figure is showing what's referred to as deferred synchronous RPCs. Here you basically have two asynchronous RPCs in reverse. So the first one is the request that comes to the server, acknowledgement goes back, the client continues execution, that's shown by the dark bold line there, and then the server is going to go off and execute the RPC. When the reply is generated, the reply is actually sent as a reverse RPC request from the server to the client, reverse asynchronous. So you get the reply and then you get an acknowledgement. Okay, and then the server continues execution. Okay, so if you have two asynchronous RPCs, one going from the client to the server, the reply going from the server to the client, you have what is called deferred synchronous RPC. The different semantics for your RPC system. Okay, the last one is referred to as one-way RPC. Essentially, the client just sends a request and doesn't even wait for an acknowledgement. Okay, it just continues. Just send off the RPC request and that's it. And then you can just continue. You don't even wait for an acknowledgement or the reply. The replies can come at an arbitrary time later. Okay? The limitation here is reliability is not guaranteed. If you are running on a non-reliable transport protocol such as UDP, you don't even know if the request was received by the server. You are not even waiting for the acknowledgement at this point. Okay? So 4 different abstractions. Okay, starting with synchronous, that's the traditional model. So asynchronous RPC, deferred synchronous RPC, one-way RPC. So there are 4 different ways you can implement your RPC system. So when you write your RPC call, you have to see what the system is providing for you. Most likely it is going to just do the standard thing, which is this, synchronous. Okay, but there are systems that will allow you to do asynchronous as well. If you want to write event-based servers, you are better off going with asynchronous RPCs, not synchronous. Okay? Any questions here? In the semantics. Okay, so now we'll look at RPCs in object-oriented world. Okay, so we understand what RPCs are. If you apply the abstraction of RPCs to objects, okay, you are essentially going to get what is referred to as remote method invocation. Same concept, okay, but except that now you have basically applications that are object-oriented. The most common use of this is in Java. Practically any object-oriented programming language that supports this notion of invoking remote methods, okay, Java being the most common one. Okay. So essentially you are going to assume that your application is written as a set of classes. Okay. When you run your application, okay, these classes are instantiated as objects. Okay. application is distributed, so some objects may be at the client, some objects may run at the server. Now essentially you are allowing a method in object 1 to invoke a method that is exported by object 2. And this is how object-oriented programming works. So if you basically call a method from a different class, except that now in this case that object belonging to that class resides on a different server, you are invoking a remote method. So there is a so this is the client program, it has object O1, two objects. So object O3 may be exporting objects that are available externally. So I might have foo here. So within O1 you might just call O3.foo, for instance. And this is like just as you would make a Java object method call on a Java object, except that the code for foo actually resides on a different machine inside a different object. Okay. So this is going to trigger equivalent of RPC call, where this request foo with any arguments is going to be sent by the stub over to the client, over to the server. Server will execute it, send back a reply, and so on. Okay. Same concept, except that these are objects that are making calls from one machine to another.
What is O2?
Sorry?
What is O2?
These are just objects. So you don't need O2 in this example. There's object O1 here, there's an object here. This object is making invoking a method, okay, on that object, except that this object is remote, a remote object, not a local object. So these are the objects reside within the same address space, they are referred to as local objects. Some objects reside elsewhere, they are referred to as remote objects. Collectively, these are referred to as distributed objects. So the code is partitioned into objects. Some code resides on one machine, some may reside on another machine, and objects can make calls on other objects. And calls are basically implemented as remote method invocations. Invocations of remote methods. Now the one major difference between RMIs and RPCs, at least Java RMIs and RPCs, is that RMIs support what are referred to as system-wide object references. Okay. They allow you to refer to objects on a system-wide basis. So what that also means is you can pass certain kinds of parameters by reference and not by value. Okay. In RPCs, we said you cannot pass pointers. Because if you have C code and you are passing a pointer, that pointer is meaningless on the other machine. Okay. In case of RMIs, okay, object references are valid system-wide, they are global and unique. So if you say object O3, okay, this object O3 is actually known to all the applications here, and you can, when you dereference that object, you can essentially figure out where it resides and call a method. Okay. So you can pass objects by reference. Okay. So which is effectively a way of passing network pointers, except that the network pointers are on objects, not on individual data structures. You can't pass an array by reference, but you can pass an object by reference, because you have system-wide object references in Java. Okay, I'm going to show you a picture to make this a little more clear. So actually two pictures. First one is a simple, the same picture I drew here on the board is the client, that's a server. The square, that shaded box is essentially, not the shaded box, the big box is an object. Okay, the object has some state, and these are methods that it exports. Okay. The methods are usually exported using an interface. The server implements an interface. Okay, just if you know anything about Java, you should know that there's an interface to a Java class and there's implementation of the Java class. Okay. So you can say this interface can be imported by any client on any machine, and you export that interface. Those would list all the methods that can be invoked. At the client end, you will first import the interface. So you will have a list of methods that the client or the server is exporting. Right. Once you do that, you can basically then take an object on the server end and then call object.foo. Okay, that's foo is a method on that server. Okay. And then you have what is called a proxy. This is the name for a stub in the Java word, which will take that method, it will construct a message, it will send the message here. It comes to the other end. The server stub is referred to as a skeleton in this terminology, and that does the same thing. It will unpack the arguments, it will invoke the method, take the results, construct another message, send it back, and so on. Same concepts, there are stubs at both ends. The client stub referred to as proxy, server stub is referred to as skeleton, and basically similar things apply in this case. And now I'll show you a picture of what I meant by this remote object references. Okay, so here we see three machines. There is an object O1 on machine A, there is object O2 on machine 2, and there is some code running on machine 3, there are no local objects there. Now suppose that you want to make a call that passes objects O1 and O2 as parameters. Okay, so let's say you want to make a such call. And that call goes from, it's a remote call, it goes from here to here. Okay. So what can happen in case of Java is that you don't have to pass all parameters by value. If you wanted to pass parameter by value, you would essentially have to take that entire object and stuff it into the parameters and send it over. Okay, because the object has state, all the internal variables of the objects are to be sent over. Okay. In case of Java, what it does is local objects are always passed by value, the remote objects are passed by reference. So when you send this request over, you will pass a pointer to this object as part of the call, but you will send a copy of this object because this object is local. So the default semantics are local objects, you pass a copy. Okay, so you take a copy of this whole thing and pass it. So here is the copy of O1 as shown up. But a remote object, you don't pass a copy, you pass a pointer. That remote object, you pass a pointer. So the server code here now has a pointer to this object. And this, more importantly, the server can dereference that pointer to that object, and that is a meaningful dereferencing of that pointer. Because you can pass by reference, pass objects by reference. Okay. Now the runtime system has to do a lot more work in terms of when you say object O2 dot method in this code here, it has to figure out that the object, where is that object O2, find the the machine IP address, the port number, all of that you have to do. Okay, so essentially you are passing what is called network pointers, okay, which can be dereferenced. Network pointer is more than a memory address. Typically it includes an IP address and a memory address and a port number and all of those things. Right. We will come back to network pointers when we do middleware. We will also see how network pointers are implemented in that context. This is also a middleware, but we will not go into the details here. Okay. So the main takeaway message is RMIs are less restrictive than RPCs. RPCs only support pass by value, passing parameters by value. RMIs allow you to pass certain kinds of parameters by reference, specifically object references. Okay, you can't pass an array by reference, but you can certainly pass a remote object by reference. Okay, that reduces the overhead of passing your parameter. It increases the complexity of the runtime system because it will need to dereference a system-wide reference to an object. Okay, is that clear? Any questions on this?
Why can't you pass array like this?
You could. I'm just telling what Java does. Right? In case of Java, basically, if you could establish system-wide references to arbitrary data structures, then you could pass anything you want by reference. What they have implemented is objects are entities that they have implemented how to dereference. Okay, so basically, and so that they allow you to pass. So if you want to pass an array by reference, it's better to make an object and put the array as a variable for that object and pass that object, a reference to that object, rather than directly passing a data structure. Because this is object oriented, that's why it's assumed that there are few global variables and all the state is captured as one object or another. Okay, so that's how you would do it.
Is it because everything runs in the same JVM? So if you're doing an RMI to, you'd be invoking another procedure which is still in the same VM?
Okay, question is this because things run in JVM and when you make an RMI call? So you have to realize that these are independent machines. Okay, okay. The Java world, each will run its own JVM. There will be some Java code running here, some Java code running here, some Java code running here. If this is the Java world. Okay, so these are not the same JVMs. Okay, so you still have to implement system-wide references, which is the equivalent of network pointers to objects. Any other questions on this? So if you write labs using Java, you can decide what you want to do, and you make, if you use RMIs for instance, whether to pass by reference or pass local objects by value, and you pay different overheads depending on what you are doing. Okay, but you have more flexibility than RPCs. In RPCs, you will not have that flexibility. By default, any parameter you pass will be copied over. As a middleware that would come standard on most Unix-like systems, there was commercial systems that used it for a while, and then it never took off, so then it silently died. Okay. But it's instructive to actually understand what kinds of object models and semantics that they actually provide. Okay. So there are two pictures shown here, and these are two different applications, client-server applications. Okay. So in both cases, the top box is a server, and these small boxes are clients. Okay. So in this case, the client-server application is implemented using what are called private objects. Whenever a request comes in for to the server, okay, the server creates a new object, okay, and then has that object service that request. This is the equivalent of creating a new thread, and then the thread goes off and services that object, that request, and then you're done. Okay, so when each new request gets a new object, there's a thread associated with that object. You take the object, which is the code for the server, and the thread executes that method in that object and sends back a reply. Okay. Requests are RMI calls, so not socket calls. Now, so these are transient. Okay, just as in a thread per request model, the thread terminates. Okay. In this case, the thread will terminate after the request is finished, and this object is basically discarded. A destructor is run on it, and it goes away. So, as you can imagine, you cannot actually include state in this server. This has to be a stateless server. But every time a new request comes in, you create a new object, a temporary object. You have a class, you instantiate an object, you have a thread, you take the object and the thread and say, go service this request. Once you're done, you sort of throw that object away. So if there is state, then the state in that object is go away as soon as the object is deallocated. If you want to keep stateful objects, you have to have what are referred to as shared objects. They're not private objects. So these are private objects, that's a shared object. Shared object is persistent, not transient. These objects are transient, they come and go as well. They basically come once and then they go away. Yes, persistent objects basically get created when the server starts up, and it stays for the lifetime of the server. So in this case, you can actually keep state in that object. You can keep variables, you can track state, and so on. And the state is not dependent on whether the client has made a request and the request is finished. The state is going to stay there. When the next client comes in, the state is going to stay in the object because the object is still alive. Okay. So you can basically use, when you write your distributed application in DC, you can say whether the RMI calls you are making go to private object or shared object. If you write a stateless server, you are better off going with private objects that get instantiated on the fly every time a request comes in. If you have a stateful server, you are better off using shared objects that persist across the lifetime of the server. Okay, they persist only in memory, but they persist across individual client requests. Okay. So you have this. So this kind of concept doesn't exist in Java at all. Okay, so it's not like the object is created on the fly and it goes away. Essentially, you assume that if the server is running and you run instantiate an object, it is going to be in this mode. Okay, so in the Java world, you are only here. DC allows you this additional flexibility of having transient objects that are private to each individual client request. They are only useful if you have stateless applications, stateless servers. Yes,
Can you have multiple copies of the same named object, because it doesn't seem like it would scale well if you couldn't.
So that's a good point. Point is, can you have multiple copies of the same object? Will it scale well? That's a good question rather. So there are many ways to scale this server. Okay. I did not show any threads here. So you can have multiple threads operating on the same object. So this could be multi-threaded server, except that all threads execute different methods on the same object. Okay, so you can have multiple threads that allow you to scale. So the requests don't have to be sequential. Okay, so you can essentially have multi-threaded. You can also have what are called replicated objects. Okay. Replicated objects are not the same as distributed objects. Distributed objects essentially says objects in the applications are just scattered across machines. Replicated objects is the same object which is replicated on the same machine on multiple machines. Right? If you have a replicated object, the runtime system has to synchronize the state of the object. Okay, it doesn't matter which copy, which replica of the object to invoke a method. If there are variables there, they will have the same value. Okay, so another way to scale is to replicate the object, something we have not yet looked at. When we go to replication, we will see distributed systems that will replicate state. Okay, so those are the two ways to scale, is to actually have threads, that's automatically there in most of these systems, and this will be the multi-threaded server. Okay, there is only one shared object. Okay, there could be more than one, but each object is shared, and there are multiple threads that may be executing methods. That allows concurrence. Okay, it doesn't allow you to scale beyond that server. If you want to scale beyond the server, you need to replicate. Okay, that adds its own level of complexity. It's the same state that you will have to keep on another machine. If a method here changes the state, that those state changes have to be propagated to the other replicas and so on. So you have to ensure consistency. Okay? All issues we will come back to later. Okay? That's why I didn't mention anything on replication at the moment. Okay? So very quickly, for those of you who know Java or might want to use it, so in the Java world, just as I showed you some RPC stuff, so the Java world, you can use RMI, it's part of the language. The way you do this is, on the server side, you first define the interface. The interface is the set of methods that the server is exporting to any client that wishes to make RMI calls. Okay. And then you have to supply an implementation of the interface. So for each method you're exporting, you write code that is going to actually implement that method. Okay, so you have this separation between interface and implementation. Okay. The interface is exported and is registered to the server. So when the server starts up, you're going to register the object with the remote object registry. Okay, that's equivalent to your directory service. When the client starts up, it has to first look up the remote object registry saying, where is this object O3 reside or foo reside? Yes, and you basically are told saying this is where the object is, and then you can go and make a call. You can establish a network connection and make a call. So there's RMI registry, which is the name server. You can have RMI compilers in Java and so on. There are many tools available that you can use to generate the stubs for your language and so on. The higher level principle is still the same, which is the programmer should program at the abstraction of writing objects and methods and invoking methods, and you don't deal with all the low level networking details of saying I need to establish a TCP connection before I can send a message. All that is still done for you by the stub code, the proxies and the skeleton code. Okay, so that code is going to be auto-generated for you. Okay. We will provide some, if you decide to go with Java, we'll provide some tutorials that will help you understand this better. If you do C, C++, we'll give you some material there. If you choose to do something else with Python or whatever, you can do that, but we can't provide you guides for every language that you pick. Okay. The two that we would think are most common would be C, C++, or Java. Okay. But you are free to use whatever programming language you want for any programming you do in this class. Okay. So one last point I want to mention about Java RMI before we move on to some other stuff is synchronization. So when you have objects that are distributed across machines, the problem of synchronization is going to be more difficult. Okay. So essentially, if you have multiple threads inside a Java program, you will have to implement locks or monitors to ensure synchronization, locks, monitors, or semaphore. What happens now when the application is split across machines? How does locking work? You still need to do synchronization. If you have shared state, multiple clients are making requests, you still need to have locks. Okay, you can't do away with synchronization. except that now you are in the distributed world. Okay, so this whole problem of synchronization becomes a lot more complicated. So we will see implementation of distributed locks when we come to the next chapter. But for the purpose of RMI, this is basically what you need to know. Okay, so you can implement locking functionality either at the client end or at the server end. Okay. The simplest thing to do. Okay, so let's say you have a server. Okay. Server has an object O and there is a stub. Okay. The simplest thing to do is implement the lock at the server end. If multiple requests come in and access to this object needs to be synchronized, each request has to grab a lock. Okay, so you say lock, grab a lock on O. And if the lock is in use, any other request is going to be blocked here until that lock is released. Okay, that's the simplest. So this is essentially you're centralizing the lock at the server side. Okay, so the first request that comes in grabs the lock, and while that request is executing, other RMI calls that are trying to access similar methods that require synchronizations are going to block. This is the simplest implementation of a lock. Okay, so this says block at the server. So you can synchronize across multiple clients. Some clients might have to wait if the lock is in use. Okay. Now, one problem is clients might crash, and then you have to deal with this problem, which we will ignore for the moment. We will not worry about failures. There are no failures. This is a fine principle. Okay, the other option is to implement locks at clients, not at the server. Okay, so the server doesn't have a lock. Okay, here are two clients, C1 and C2. Okay, so there are two stubs. So there is lock code here, and these two clients are going to coordinate the lock. Okay, so client 1 says, I want the lock, and if the lock is free, it will grab the lock. And then if client C2 decides it wants the lock, it will have to wait. Okay. So this lock is basically a distributed lock. Okay, the implementation of the lock is distributed. It's logically one lock, but the code is distributed. Okay, so you want to basically implement a lock in a distributed fashion. So if you do locking at the client end rather at the server end, you have to implement this locks in a distributed fashion. How to do this, we'll see in the next chapter. If you do locking at the server end, this is standard centralized locks, the same kind of lock you probably heard of already. Just have to implement that or implement a monitor that will do the locking for you. Okay, so I'm going to spend the next few minutes just talking about vanilla socket communication. So we have done RPCs, we have done RMIs. Okay, for those of you who decide that you don't want to use either, you want to use your own sockets for any programming, you basically have to write your code at a much lower level, okay, which is at the socket level. Whether it's Java sockets or sockets in C, C++, it doesn't matter. You basically have to follow the same kind of principles. Okay. So this is basically a flow chart of what the server does to enable network communication. There is a flow chart of what is happening at the client. And these are sequence of calls that the server and the client have to execute. Okay. So what happens is first the server, so if the client and the server want to establish communication, each has to instantiate a socket, and then you have to connect the sockets together. And that's the way this works is the client will make a socket system call that will give you a new socket. Okay, this is where you can specify whether it should be TCP or UDP and things like that. Once your socket endpoint has been established, you are going to want to connect to the server. And this is, you will write call the connect call that will try to connect to the server and establish a TCP connection, for instance. In this case, this is all TCP. At the server end, what you will do is you will also instantiate a socket. You will bind that socket to a port number. Okay, so if you are HTTP server, this is going to bind that socket to port 80, saying that's the port at which I'm going to listen on. Okay. Then you basically call the listen, which says now I'm willing to start listening on to this port that is specified in the bind call, and then you wait for any new request to come. And that basically you call accept, saying accept a new request. Okay. And until a client tries to connect, this accept will block, waiting for a client request to come in. And if some client here, for instance, this client calls connect, this is where the client and the server actually establish communication. So you basically send a connect, it goes to the accept call. At this point, the client and server have established a connection. You can use read and write calls to write to a socket and read back from the socket. Sockets are duplex. You can write to it and read from it, just as you can write to a file and read from a file. Okay. So this is basically, you'll do this in a loop. You'll send some number of messages and get some number of replies, and then you'll close the socket. Okay. If you program at a socket level, you have to write all of that code. Okay. As I was mentioning, if you do this at the RPC level, the stub does all of the stuff. Your code will still do the same thing, except that the stub will auto-generate code to do this for you. So depending on what level of flexibility you want versus convenience, you can decide that you offload this task to the stub, or you decide that you want to do it yourself. It's not difficult, but somebody has to write the code. That somebody is a compiler or the programmer. So this is basically the way typically sockets work. And this is just a table that shows all of those calls that I mentioned there. As a socket creates a new communication endpoint, bind will attach a local address, which is a port number, to the socket. Okay, listen basically announces your willingness to receive new connection, and accept is a blocking call. It's going to block the caller until a request actually arrives at that port you're bound to. Okay. Connect is instead sort of triggered by a client, where you try to establish a connection to the other end, and then you can use either send, receive, or read, write. They are roughly equivalent in what you do. You can use a send call to send data and a receive call to receive data, or you can use read and write to read or write, and both can give you equivalent functionality. Okay. So just something you should know whether you use it or not. And the reason we need to sort of understand this is, we will now talk a little bit about this other library called MPI that also enables communication, but it generalizes this notion, and we'll see how. So MPI stands for Message Passing Interface. It is basically a middleware that is implemented for high performance communication. Okay, so when people have an application that is running in parallel on lots of machines, okay, and doing some high performance computation, whether it's some astronomy computation or physics computation, or we were doing some bioinformatics computation on lots and lots of data. Each of these processes that are running on this machine have to send messages to coordinate the entire task, entire computation. MPI happens to be a popular library or a middleware that is used to instantiate such communication. Okay. And we'll see why. MPI can actually give you better abstractions or lower overhead abstraction than standard TCP/IP. Okay. So it is used in a cluster of servers, and it is basically what MPI stands for Message Passing Interface. It is designed for parallel applications and what is referred to as transient communication. So I'll show you some examples primitives. And we are not going to go into a lot of details into MPI. Neither do you have to program using MPI. It's just good to understand what it does, okay, and how it generalizes the notion of Berkeley sockets. So here are basically the calls that MPI will support. So there is something called a bsend call, which says append an outgoing message to a send buffer. Okay. There's a send call which says send a message and wait until the message is actually being copied to a remote buffer. Okay. There is something called send, which is send a message and wait until the reply comes back, and then wait until the receipt of that message starts. And send receive says send a message and wait for the reply to come back. So there are 4 flavors of a send call. In sockets, you basically have just one. You can either say send or write. In MPI, you have 4 different calls to send a message from one machine to another. Now, so you should ask, what do these things do? Okay, what is the difference between all of them? Okay, wait for you to look at it. So maybe you can think about what each call is saying and what does it do for us.
like first one is not depending on whether client is like active or not.
Okay, first one is not dependent on what, so let's pause. Let's just draw a picture here. So let's call them sender a client and the recipient a server. Okay, so what did you say is the first one?
Like first one doesn't depend whether the client received the message like right away or.
Alright, so the first one basically doesn't depend on whether the client, not the client, the other end received the message. All it is saying is the send call is just going to copy the message to the local buffer, and the call is going to return, and you are going to continue execution.
So you're not actually sending it right now.
You will send it, but the client is not going to wait for the message to go across. So what does this remind? So let's say look at the next one and then see if this is sort of, we can map this one. So what does the send do? Send says send a message and wait for it to be copied to the remote buffer. Okay, let's forget the local buffer. So in the second one, you basically construct a message and you wait for it to be copied to the OS at the other end, and then you continue execution. Okay. What send does is you send a message and wait for it until receipt starts. You don't wait just until it reaches the OS buffer. You will actually wait until the server process has actually done a receipt. It has actually received the buffer, and then you just continue. Okay. And send receives send a message and wait for the reply. Okay, so not only do you copy it to the local buffer, not only do you wait it until it reaches the OS at the other end, you wait until the other end has actually received it, processed it, and then send back a reply. Okay. So if you just think about it, you will see that this nicely maps into the 4 RPC semantics I mentioned at the beginning. Okay. The top one is one-way, what is equivalent to one-way RPC. You just send a message, you don't even wait until it gets to the other. One of them is, these two roughly map to asynchronous RPCs. You wait for the message to have been received at the other end and you continue. The last one is synchronous RPCs. This is a full blocking call where you send the request, you wait for the message to have been received, processed, and you wait for a reply. Okay. So what this library is doing is it's giving you multiple abstractions, saying what do you really need to do. You really want to wait for the reply? Do you just want to know that the reply has gotten to the other machine? Do you want to know the reply has gotten to the other machine and the process on that machine? Or do you just want to send it and not worry about it at all and just wait for everything to happen asynchronously? So if you write an MPI application, you get all these choices. Okay. When you use vanilla sockets, you only have blocking calls. Okay. You don't get to say, I just want my socket data to have been copied into my local OS buffer and return. It's not asynchronous in that sense, it's only synchronous, so there's only one abstraction. In MPI, you get all these other abstractions as well. Okay, so a lot more flexible. You can write better, higher performing applications by picking the right abstraction that you need. Okay. So although I mentioned those 4 semantics in the RPC context, they're actually implemented in MPI. MPI is a very widely used library. If you go to any other science department where they use any computational systems, whether you go to physics or chemistry or biology, and they have code, and the code is running on a cluster, they typically would have used MPI to write their code. And this is a very common library that's used for a variety of parallel computing applications, typically high performance computing applications. Okay, so here's something to realize. And then there are equivalent, there are others, which I did not mention here. This is basically saying pass a reference to an outgoing message. So you say don't even copy the message, pass a pointer. And then you just try to dereference the pointer, and then this is basically saying pass a reference and wait until the receipt starts. Okay. And the receipt is also blocking or non-blocking. So if you do the standard receive, so receive a message and otherwise block until a message arrives. Okay, I receive says check, just basically check if there is a message. If so, get it. If not, just come back saying there is no message. Don't block. Okay, so it's a blocking version of a receive and a non-blocking version of a receive. So lot more flexibility in whether you want to use synchronous calls, asynchronous calls. to write your applications. So this gives you more flexibility in what you are trying to achieve as an application programmer. Okay. So we will stop here for today. Okay, the main to-do is to go look at the lab that I put up, okay, and hopefully get some work going on it. Next week I'm going to spend a few minutes discussing. So come back with questions, specifically if there's something. There is also the forum that you can post questions to, or of course you can come and talk to me, but it would be good if you can post it or come into class and ask, so everybody benefits from whatever clarifications any one of you needs. The lab is due in 2 weeks, Friday, 2 weeks from this Friday. Okay, so that's 2 weeks and 2 days. Okay, so let's stop here.